Hello friends, I hope you all are doing well. In this presentation, I am going to discuss different magnetic materials and their properties. Magnetic materials are those that can either be attracted or repelled when placed in an external magnetic field and can get magnetized themselves. All the materials may be classified into 5 categories from the point of view of their magnetic properties on the basis of their relative permeability. The classification is as under diamagnetic materials, paramagnetic materials, ferromagnetic materials, ferrimagnetic materials, and superparamagnetic materials. I'm going to discuss them one by one, but before that, let us discuss what is relative permeability. Permeability is the measure of the degree of magnetization that a material obtains in response to an applied magnetic field. The relative permeability of the material is the ratio of the permeability of any medium to the permeability of air or vacuum. The greater the magnetic permeability of the material, the greater the conductivity of magnetic lines of force and vice versa. और in short, material की permeability जितनी ज़्यादा होगी, उसकी magnetize होने की tendency उतनी ही ज़्यादा रहेगी. Now we are going to discuss the materials, the various magnetic materials one by one. So starting up with diamagnetic material, they have their relative permeability slightly less than 1. They are poor conductor for flux lines than that of the air, so they can never be used as a magnet, and they are repelled by the magnetic field if they are placed inside the magnetic field. Whereas paramagnetic material is concerned, they have their relative permeability slightly greater than 1. They are slightly better conductors for the flux lines than that of the air. They can also not be used for the manufacture of magnets because of their poor magnetic properties. Talking about ferromagnetic materials, they have very high relative permeability, maybe of the order of 10 to the power 2 to 10 to the power 3, and they are used for magnets, either permanent or electromagnets, very frequently. They further can be subdivided into hard and soft materials. Hard ferromagnetic material include permanent magnet materials such as alnico, chromium steels, certain copper nickel alloys, and several other metal alloys. Whereas soft ferromagnetic materials include iron and its several alloys with nickel, cobalt, tungsten, and aluminium. Silicon steels and cast steels are the most important ferromagnetic materials to be used as electromagnets in the transformer and rotating electric machines. Coming to the ferromagnetic materials, they are ferrites and composed of the iron oxides, and they also have very high relative permeability, maybe of the order of 10 to the power 2 to 10 to the power 3. They are used for magnets undergoing high frequencies very frequently. They further may be subdivided into hard and soft materials. Hard ferromagnetic materials include permanent magnet materials, and soft ferromagnetic materials include nickel zinc and manganese zinc ferrites. They are quite useful in high frequency transformers, microwave device, and other high frequency applications. Now coming to superparamagnetic materials, they are made from powdered iron or other magnetic particles. They also have very high relative permeability, maybe of the order of 10 to the power 2 to 10 to the power 3. These materials are used in transformers for electronics and core for the inductors. The permalloy is the best known example of superparamagnetic material. Now moving on to a very important topic, that is the properties of magnetic materials. All the magnetic materials are characterized by their non-linear BH relationship, which shows both the saturation as well as hysteresis. This phenomenon may be explained with the help of small magnetic dipoles at the molecular and atomic level. The small atomic dipoles are randomly distributed inside a magnetic material as shown in the figure under its never magnetized state, and hence we can see the net dipole moment of the material is zero. Whereas the figure B shows the net dipole moment under the pressure of the field, resulting in some non-zero dipole moment. The magnetizing cycle for a magnetic material is explained with the help of a BH curve, and it is also known as hysteresis curve or loop of the magnetic material. So we are going to discuss it in detail. When the magnetic material is excited first time as electromagnet, it traverses along the curve along OA. Once all the small dipoles are aligned in one direction due to magnetization, the magnetic core gets saturated and flux density does not increase further even with further increase in the exciting current. Now, if we start to decrease the exciting current, it traverses a new path ACD, and at point C, even if exciting current is zero, flux is not at zero value. This property of magnetic material is known as retentivity, and the non-zero flux in the core at point C, while exciting current is zero, is known as residual flux, which remains in the ion for a long time even after the removal of excitation. Further, if we increase the current in opposite direction at point D, flux is zero but at a negative value of current. This property of material is known as coercivity. The forces of current in opposite direction due to which the zero flux has been achieved are known as coercive forces. On further increasing the current in opposite direction, magnetic core gets saturated in opposite direction also along the path DE. Now, if we start reducing the current, then zero current, and then increase the current in positive direction, the curve traces the path along EFGA and hysteresis loop gets completed. Now onwards, the magnetic material under magnetization will trace the loop ACD EFGA indefinitely on each cycle of reversal of current. The BH relationship for cyclic H, as discussed in the previous slide, is also known as hysteresis loop, and it denotes the work done that is lost in aligning the small atomic dipoles of magnetic material in either direction. This lost work done appears as heat in the magnetic material and is known as hysteresis loss. The hysteresis loss in the magnetic material depends on the magnetic properties of the material as well as the amount of flux at which it is being operated. Hysteresis loss can be reduced by selecting a material with smaller area of hysteresis loop depending on the requirement or compromise between losses and the residual magnetism required. It may be easily be observed from the hysteresis loop that B is a symmetrical two-valued function of H. It may be easily recognized as a memory type nonlinearity in which the material remembers its previous history. The initial part of the BH loop, as shown in the figure, is also known as magnetizing curve of the magnetic material. Only this initial part of the BH loop, that is the magnetization curve of the magnetic material, is the subject of interest of the electrical engineers. The loss shown by the hysteresis loop combined with the eddy current losses are known as the coal losses or the iron losses. Now moving on to the eddy current and the associated losses. The eddy current losses in the magnetic material are due to the currents flowing inside the magnetic material in the form of circular currents because of the induced EMF due to changing or alternating flux. When the magnetic material is exposed to the changing flux, maybe magnetic material rotating in a magnetic field, as in the case of generator, or the field is changing but magnetic material is stationary, like in the case of transformer. An EMF is induced inside the magnetic material and the circular currents start to flow internally in the magnetic material due to this induced EMF. These circular currents in the form of eddies ultimately causes the rise in temperature of the magnetic material and hence are known as eddy current losses. These eddy current losses may be reduced by using laminated steel punching or stamping made up of high silicon steel, which is a high resistivity material as shown in the figure, in place of a solid iron body for magnetizing the core. These laminated steel punching are insulated from one another by a thin layer of varnish or resin to confine the eddy currents in individual sheets. This confinement of currents within a thin sheet will reduce its effective cross sectional area and increase the resistance of current path. The increased resistance of the current path reduces the eddy currents and hence the eddy current losses. Now, what is magnetostriction? The ferromagnetic material undergoes small changes in their dimensions when they are subjected to the magnetizing MMF. A lengthwise as well as transverse change of opposite sign takes place simultaneously. These changes are caused by magnetostriction. They are of hysteric nature and hence the dissipation of energy takes place when magnetization is alternating. These dimensional changes due to magnetostriction are associated with mechanical stress, which produces noise in the audible bandwidth. This noise may be nuisance for high flux densities employed in transformers in modern practice. The noise due to magnetostriction may therefore be the subject of limiting specifications in the transformer manufacturing. Now we are going to discuss something about permanent magnets. These are the most common type of magnets that we know and interact in our daily life. These magnets are permanent in the sense that once they have been magnetized, they retain a certain degree of magnetism and do not lose its magnetic properties over the time period. The permanent magnets are generally made up of ferromagnetic materials, and such materials consist of atoms and molecules, each having a magnetic field and are positioned to reinforce each other with the help of electromagnetism. They have high residual flux and got permanently magnetized once exposed to electromagnetism and retain their magnetic properties. Permanent magnets can further be classified into following four types based on their composition. The permanent magnets can be made into any imaginable shape. They can be made into round bars, rectangular bar magnet, horseshoe magnet, donut or ring magnet, disc magnet as shown in the slide, and other custom shapes also as and when required. While the shape of the magnet is important aesthetically and sometimes for experimentation, how the magnet is magnetized is equally important. For example, a ring magnet may be magnetized south pole on inside and north on outside, or N on one edge and S on the other, or N on the top side and S on the bottom. Depending on the end usage, the shape and configuration of the magnet vary. Now we are going to discuss that how we can demagnetize a permanent magnet. The permanent magnet gets demagnetized or they get weak over a long time period due to Earth's magnetic and stray magnetic fields of strong electromagnets in the vicinity. The forced demagnetization of the permanent magnet may also be done using following methods. Using heat. The heating of a magnet until it got red hot makes it lose its magnetic properties. Contact with another magnet. Stroking one magnet with another strong magnet in a random fashion will also demagnetize the magnet being stroked. Hammering or jarring. The continuous hammering of a magnet will loosen its magnet's atoms from its magnetic attraction and magnet will get demagnetized. Electromagnetism. The magnet can be demagnetized providing its coercive forces in negative direction by a negative magnetizing current as per the BH loop of the magnetic material, and it gets permanently and completely demagnetized. The temporary magnets are those materials which act like permanent magnet when they lie within a strong magnetic field. Unlike permanent magnets, however, they lose their magnetism when the field disappears. We would have been deprived of many luxuries and necessities in life, including computers, television, telephones, mobile phones, computer printers, washing machines, refrigerators, washing machines, fans, pumps, mixer grinders, vacuum cleaners, and so many other daily necessities without the electromagnets. The electromagnets are extremely strong magnets and they are very useful. They are produced by placing a magnetic core inside a coil of wire carrying an electric current. The flow of electric current in the coil produces a magnetic field inside the metal core to make it strong electromagnet depending on the current flowing and the number of turns of the coil. So, the strength of the magnet is directly proportional to the intensity of the current and the number of turns in the coil. Its polarity depends on the direction of the flow of current, which is given by the right hand thumb rule or right hand screw rule. Now, what is right hand thumb rule? When a conductor carries a current in a certain direction, a magnetic field is being produced by this current given by the right hand screw rule. That is, if we hold the current carrying conductor in our right hand, pointing the thumb in the direction of the flow of current, the direction of our right hand fingers will give the direction of the magnetic field in circular shape around the conductor. Now, this rule is vice versa. So, if the figures are indicating the direction of the current, the thumb direction shows the direction of the magnetic field produced. The core behaves like a magnet when the current continues to flow. However, as soon as the flow of current is interrupted, the core is demagnetized and behaves like normal metal piece. But a small residual magnetism resides inside the metal piece depending on its BH loop. Electromagnets are most useful when the magnet must be switched on and off as in motor during its operation. Large cranes used to lift cables and rods in construction. So I hope this video was helpful to you. See you in the next one. Till then, take care.